So we're going to head and look at exponential functions now. And again, we've looked at a little bit with certainly dealing with exponents that are integers, something like 8 squared. That's 8 times 8, 64. Integral exponents 8 to the 2/3. We can rewrite that as the cube root of 8 squared. 2 squared is 4. But what would something like 8 to the 1.7 be equal to? It's not 8 times 8. It's somewhere, we might guess it's going to be, since 1.7 is in between 1 and 2, 8 to the 1.7 will somewhere be in between 8 to the first and 8 squared. If we looked at a specific exponential function like 2 to the x, we could simply plot some points and then ask ourselves what's reasonable to happen in between those points, and that's kind of what we're going to do for now. So if I look at f of x equals 2 to the x, 2 to the 0 is 1, so I know I have y-intercept here, 0, 1. 2 to the first is 2, 2 squared is 4, 2 cubed is 8. And if I come down, 2 to the negative 1 is 1 over 2 to the first is a half. 2 to the negative 2 is 1 over 2 squared is a fourth. And at negative 3, that would be 2 to the negative 3, or 1 over 2 cubed, which would be 1/8. And then if I look at that and say, well, if those are my specific points, if I were to look at x values in between those integers, it would be reasonable, and indeed it's going to turn out that a smooth curve is going to connect them. So it is going to make sense for us to look at something like 2 to the 1.35. And we're going to use our calculator to help us get decimal approximations for such expressions. So our text is going to define an exponential function to be in the form of a times b to the x, where they've said that a is going to be greater than 0. Arguably, if a were less than 0, negative 2 or negative 3 or negative 4, that's going to simply flip an exponential function over the x-axis. So while they've defined it to be a is greater than 0, certainly we're not going to have any difficulty with functions where a is less than 0. And then b, however, is greater than 0. Our base is going to be bigger than 0, and our base cannot equal to 1. Clearly 1 to any power is 1, and that would be a pretty dull function. 7 times 1 to the x is simply going to be 1 raised to any power. Wherever I put for x in, I'm going to get 1 to that power, which is 1, so that's just going to be a horizontal line at y equals 1. Not an interesting function. Where b equals 1, that's not going to be considered to be an exponential function. So some examples of exponential functions: 2 times 3 to the x, 1/2 times 1/2 raised to the x power. And note with this last function here, I could rewrite that as 0.5. 1/2 is 2 to the negative 1 to the x, which is 0.5 raised 2 to the negative x. And I want to think about how that might compare to an exponential function 0.5 times 2 to the positive x. Remember, if I replace x with negative x, that's going to reflect over the y-axis. So some of these functions from our rules before, for translating or for stretching or shrinking, we're going to be able to look at a basic exponential function and see what a modified function will look like, considering back what we learned about horizontal stretches and shrinks and vertical stretches and shrinks, and reflections about the x-axis and y-axis, etc., etc. So in 5.3 here, we're going to talk about a couple different formulas, ways to look at our exponential growth that we've seen before in the context of annual appreciation. Just look at it a little differently. For example, let's suppose I have $1,000. It's growing 7% per year, and I want to know how much I've got after t years. What we've done before is said, look, if we grow by 7%, we multiply by 1.07, so the amount I've got after my t years is going to be my initial amount, 1,000, times 1.07 raised to the t. In the financial world, they like to look at this as a formula where they're going to include that 1.07 multiplicative factor viewed as a 1 plus a rate. So if they say, hey, you're growing by 7% per year, write that 7% divide by 100 as 0.07. So then you're going to rewrite this as 1,000, 1 plus 0.07, and then you get to the same answer. It's just viewing the formula, and rather than looking at it as a multiplicative factor by 1.07, it's a 1 plus a growth rate. I prefer this method if you understand what we did before, then it's going to be pretty easy to see why and where the financial formula comes from. So suppose we've got $100, it grows to triples, goes to $300 in 6 years under a certain annual rate of growth. Suppose I want to find a rule for the amount I've got after time t using my exponential function. Well, I then know that 300 is going to equal the amount I started with, 100 times b raised to some exponent. In this case, in 6 years we've gone to 300, so 100b to the sixth. Go ahead and solve for b. Divide each side by 100, you get 3 equals b to the sixth. Solve for b, take the sixth root of each side, 3 to the 1/6 equals b. So my exponential growth rate here, function, would be the amount I've got after t years is my initial amount times 3 to the 1/6 raised to the t power. Go ahead and use your law of exponents here to write that as t over 6, and I get my rule as the initial amount times 3 raised to the t over 6 power. And looking at your initial situation up here, you'll note that we are tripling, and we have a 3 appearing here, and we have that tripling occur in 6 years, and we have divided by 6 in our exponent. So therefore, if you look at page 181, they give you a formula in red, number 2, that gives you a formula for a time needed to multiply an initial amount by some value b. So this can also work if things are decreasing in size. Next slide. So we can also have populations or amounts rather than increasing, they can decrease. One application of this occurs in science quite a bit. Half-lives of things, which is the amount of time it takes for my population to reduce by a factor of 1/2, meaning I'd multiply the population by 1/2. So according to my formula, the amount of, this is the formula on page 181 in red in the middle of the page, the amount that I have after t, amount of time t, is going to be the initial amount times my multiplicative factor raised to the time over the amount of time it takes to carry out that increase or decrease of population. So in this case, if I have a half-life of 50 years, my b is going to be 1/2. The time it takes to reduce by 1/2 is 50, so the amount I have after t years would be my initial amount times 1/2 raised to the t over 50. And if I think about that, that should make some sense. For example, if I let t equals 50, 50 over 50 is 1. 1/2 to the first is 1/2. So a naught times 1/2 would be indeed, after 50 years, I'd have half of what I started with. You could go ahead and put a 2 in, and that, if you put a 2 in, you're looking at a naught to the 1/2, putting 100 in, you're looking at 100 over 50 is 2. That's a naught times 1/2 times 1/2. And if you think about 100 years, your first 100 years, your population is going to, in that 100 years, your population over the first 50 years is going to drop by 1/2. So that's a naught times 1/2. Now you got your new population of a naught times 1/2. 50 more years go by, you're going to reduce it by a half again. You'd have to multiply by half again. So you'd have a naught times 1/2 times your next 1/2. So that, again, that formula should make some sense.